6 p.m. So we can start our today's discussion. So very good evening, Ahmed. So in right now we are in the week 7.
Yes, good evening.
Good evening to you. Week 7 of the Technique of Material Characterization course. Let's see the list of the topic that has been covered in this particular week. What we have studied is about the secondary electron detector. We learned in detail about the Everhard Thorne detector. Then we learn about the scintillator that has been used for the BSC detector. Also, then we studied about the solid state BSC detector, and then we went to the SEM optics. So we spent around 2 to 3 lectures in the SEM optics, and we studied in depth about the depth of field, resolutions. Those things has been covered. So before I start with the Q&A sessions and solving the questions, I would like to ask you, do you have any doubt in this particular week, whatever has been covered by the professor or whatever has been covered till now?
I am little confused because, and I'm filling the assignment work, and I'm keep watching again and again that lecturer. One question I'm unable to conclude myself. That, that is the inline detector. It's covered with SE1 and SE2. But is it true, or we need to consider because majority of the SC1 is covered, so we can consider it is made for only inland detector for SC1 only. So that's a confusion only I have.
Okay, so this has been covered in the class. So what professor has told us that the inline detector is used to improve the resolution of the SE. But after that, he told that okay, it is why it is happening, why the resolution is increasing, because we are mostly focused on the narrow range of the that secondary electron which is coming from the SE1. So there are the two things, SE1 and SE2. So here, if we take our interaction volume, SE1 will come from here and the SE2 will be somewhere coming over here. So this inline detector, it is majority is phased is determined by the SE1. Very small insignificant amount of signal is also considered from the SE2. Okay, but majorly on the larger scale it is by the SE1.
Yeah.
Yep.
But when it is question comes like inland detector for SE1, SE2, SE1 and SE2 both. So which is the right answer? Because it will works also SE2. I believe slightly it works.
Okay. Mm, SE2 also it take the but its essence is majorly based on the SE1. But yeah, your concern is also right that the if in the assignments both are mentioned, one is separately SE1 and the another is SE1 and SE2, then what should we go for? Uh, I
Because the chat GPT DeepSeek also confused me.
Yep.
It is giving SC1 and both also. And I'm saying you are wrong. I think this is SC1 is right means then he's saying yes, appreciated, SC1 is right. Then when he's giving that one, no, you are wrong, both is works, then he's saying yes, you are right, both is right. So both DeepSeek and ChatGPT are also confusing. Even Google Chat also it is saying SC1 and SC2. And I'm listening the video again and again. The lecturer also said little SE2 will also will contribute in inline detector. That can be avoidable. That cannot be avoidable. It will be. But majority 90% SE1. So coming to the answer to the question, really, I don't have any rigid answer here.
Yep. It's very Like this question is quite, the option is quite in dilemma, which one to take. So what I will suggest you that, since I cannot answer, I would suggest you that your query, whatever you are facing, I would appreciate that you write in the doubt forum, and so that we can discuss with the professor regarding this. Like the options are quite confusing, because the both the answer seems like it's correct, and you think like which one should we go for, right? Because both of them are contributing to certain extent, even though SE2 is very less, but it is there. So should we go with the both of them to be correct, or only one of them to be the correct? So this dilemma which you are having, I would, it would be great if you write it up in the Q&A forum.
Okay.
Yeah.
Okay.
So very good evening everyone. So these are the list of the concept that has been covered in this class. We talked about the SE detector, we talked about the BSE detector, both the type of BSE detector we talk about. And then after that, we focus majorly on the SCM optics. So if there is any doubt, guys, let me know in the concept that has been covered. If not, we can always we can go ahead and try to solve few questions and discuss few concepts based on the information that we have covered. Let's have a, since there is no doubt, let's revisit the part of the ET detector, which is primarily we use it for the, like currently nowadays we use it for the secondary electron. So what is happening here? We are capturing the secondary electron which is having the energy less than 50 electron volt, which we have talked in the last week also. The specimen, the electron beam is interacting with the specimen, and various backscattered and SE signals are created. Now those signals we have to detect. So let us say our purpose is to detect the secondary electron, so we'll use this ET detector. What it will do, first of all, it has a cage. This is the entire thing is known as the ET detector. It will have a cage. The cage will be positive biased. Okay, forget about this negative part. It will be positive biased by a certain value, maybe 250, or you can say in the class we have saw that it is around 300. It vary from SEM to SEM, but more or less it will be around this. Now electron is having negative charge, and this is having the positive bias, so it will attract it, right? So we will be able to capture the electrons, secondary electrons having the low energy. Why this voltage is needed? Why electron was not directly coming? It was because the energy was very less, the secondary electron having less energy. So this less energy needs some driving force to be collected at the detector. So this is why this cage is needed. This cage of around 150 or 300 volt is needed. Now the beam has entered. Now the electrons has entered from the specimen. Now we need to convert this signal. First, what scintillator will do? It has the cover of aluminum foil, which is having the positive 12 kV electron, sorry, 12 kV voltage. This much of bias is there. Note, remember that whenever we are talking about the bias, something is at the positive or the higher voltage, we should also know what is at the ground. What is at the ground voltage? The specimen stage, this is at the ground. So they are at the positive bias with respect to this thing. Now, see this much high voltage we have applied. So what will happen? The electron which is entered, the electron which has entered this cage, now they will accelerate it toward the scintillator. considering this particular bias. Now this phenomena of phosphorescence will happen, and the material will absorb this detector will absorb those electrons. The material will undergo the high excitation. Like every, we know that whenever some energy we get, even the light, even the X-ray, anything, if the material is getting that energy, it will excite. The electron will excite from lower energy state to high energy state. Now, after that excitation, we know that the energy will be released because it need to get back to the ground state. Okay, so that released energy. So what we did, we got the electron signal. So what we got the electrons, which was the secondary electron. We have accelerated it. We made it SE. That is SE electron which we have got. We have accelerated it. After that much acceleration, what is happened that it excited this particular scintillator, which is phosphorus. And after that excitation, we got that the signal is converted to the light. Okay, it will convert it to the optic pulse. Now this light, this energy which has been created, now it will transmit through this. This is made up of the quartz tube. Okay, so we know the phenomena like the fiber optics, how it happened. It's same. So it will transfer this particular light which has been created by the phosphorescence. It will go to over here. Okay, photomultiplier. So now what this photomultiplier will do, it will convert that light signal, light pulse, optics pulse, to the again electric pulse. So we got this electric pulse. Now this electric pulse, we will be able to detect it on the screen. Okay. So this is how the entire scenario has been played. We had the electron, we got the signal from the specimen, that SE signal having the low energy, we excited it. So first we applied the bias to the cage so that this SE electron get attracted to it. We applied something around 250 to 300, one can say. And once this electron, the secondary electron, entered this particular cage, we are exciting it. Sorry, we are accelerating it with this particular bias. Okay, 12 kb. In class we have saw it's written as 10 kb. So both are fine. Okay. Now after that fluorescence phenomena happen, now the emission, the light will be emitted once the electron is excited to the highest energy state, and then that light which is emitted, it will transfer through this particular light guide to a photomultiplier which will convert the light signal to the electric pulse signal, right? So this is the entire behavior, the way we are detecting the SE signal. Now, if any doubt in this particular explanation, let me know. If not, let's try to solve few questions based on this particular concept that we have revised just now. Okay, since there is no doubt.
Here, I have one doubt.
Yeah.
Here, usually the specimen, it is exactly in the smooth surface, but here the specimen is slanted some extent to catch this ET detectors. So, so in SEM, really we have that option to fix the specimen in different angle, or this is the fixed platform. There is adjustment options are available. That's my question.
Yeah, very good. Actually, the specimen is here is not tilted, even though we have provision in the SEM to tilt the specimens, but in the SE we are not tilting. Why I draw a specimen like this? It is because in our specimen we have hills and valleys. So what it signify that, let's say my detector is somewhere over here. So the detector is put at certain angle. Now this detector will try to, now the beam came, now it excited, like the secondary electrons are coming. So from the region which is facing the detector will be more brighter, like we will get more electron from it, while which is at the back will get less, right? It's difficult to convert them. Even they will also come, but the energy with which they are coming, like the frequency, the number of signals that we are getting is quite less from the here. So the entire purpose why I tilted is like, okay, to show the geometry that, okay, the region which is facing the detector, it will attract more electrons compared to the which is at the far. Even though we have the provision to tilt, we are not tilting it. Okay, so this is not tilted specimen, we are just keeping it as it is. And the detector which is there, it is at certain angle. Now it will collect the electrons. Okay, you will know that in the case of when we discuss about ABSD in the last week, there we have to tilt the specimen by a certain angle. In that case, that stage will be able to move it. Okay, so that facilities are there, but we are not doing in the case of a secondary electron. Okay, great. Let's try to solve the questions. The first question is that the ET detector in the SEM is efficient in collecting backscattered electron, characteristic X-ray, Auger electron, or secondary electron. The word efficient I have used. What do you think? ET detector in SEM is efficient in collecting which one? Whether the backscattered electron, Auger electron, characteristic X-ray, and the secondary electron. Very good, Ahmed. That's right. The right answer is option D. So we know that this ET detector, which we just talked about, it is used to detect the secondary electron. Now, one can also say that, tell that, okay, previously in the past, like long back, even the BSC signal was also used to get, right? We can also get it. BSC signals also we can get. But I use the word efficient. Efficiently, it can go for the SE. Okay. So this is how it should be. The question should have some adjective or some, it should give some signal that, okay, to which direction we are going. Okay, very good. Okay, that's, with that we have solved the question number 1. Let's go ahead. Let's go to the question number 2. Now here, choose the correct statement. The scintillator material of the ET detector has the high reflective index. The scintillator material of the ET detector has the low refractive index. Okay, high, low. The scintillator material of the ET detector has the high dielectric constant. Dielectric constant. The signal generation from the scintillator material of the ET detector has no dependence on the refractive index. No dependence. What do you think? What will be the right answer? So we are talking about the scintillator. So as you know that this scintillator, here we are having something like this light guide is there. Now a light guide will be able to be some, you might have learned about the total internal refraction, something. Total internal refraction, right? It is made up of that light guide is made up of quartz, and it's usually have very high refractive index, and it is needed. Okay, this is the core of this scintillator, that how we can guide the light beam. Okay, so this is the right answer is option A here. Okay, so always remember the high refractive index is needed in the scintillator material, which is we are using the quartz. Very good, guys. Let's go to the next question. Question number 3. Now this one is very interesting. Have a look. The the plus 10 kV bias applied to the scintillator in the ET detector is used to. Why we are applying this much bias? First one, repel the secondary electron. Accelerate the low energy secondary electron so that they can generate the light in the scintillator. C, attract the backscattered electron. D, focus the primary electron beam. What do you think? What will be the right answer here? Focus the primary electron beam. See, that much voltage, like focus the primary electron beam, that will be done by the objective lens. Okay, the plus 10 kV apply to the scintillator. So we are talking about this part, that we are applying the plus 12 kV or plus 10 kV to the scintillator. Why we are doing that? The electron is captured. The now the electron has got in the cage. Now still they don't have sufficient amount of energy so that they can react. They can excite the electron of the fluorescence material, right? So now to provide that energy, sufficient energy, we need this much acceleration, 12 kV. Okay. So here the right answer will be answer B. Okay. So see, from the material we are getting the secondary electron. This secondary electron is going to the cage, which is having the around plus 300 voltage of field. Now we will accelerate it by the something around 12 kV voltage, which is applied to the aluminum foil, which is just near to the scintillator. Now this much energy we are providing so that it can excite the fluorescence phenomena is shown. Phosphorescence, sorry, not fluorescence, I pronounced it wrong. So now once it is shown, now we can get the light, which is passing through the light guide, and now then it will reach to the photomultiplier. Okay, this is the entire thing which is happening in this thing. So right now we were discussing about this thing. We need this much acceleration so that we can generate this phenomena of phosphorescence. Very good. So the right answer here is option B. Okay guys, let's, if any doubt, feel free to interrupt me in between and ask your questions. If not, let's move to the next question, question number 4. Now, why is the ET detector collection efficiency for BSc generally poor? Why it is poor? If I am using the ET detector for to collect the BSc, why it is poor? BSc has the too much energy for scintillator to handle. Second, BSc are generated close to the primary beam, but the ET detector is placed at an angle to optimize SE contrast. Third, the photomultiplier tube cannot amplify BSc signal. Fourth one, BSc signals are weaker than the SE signal. Let's try to cancel out few options. Fourth one we can cancel. BSc signals are weaker than the SE signals. No, they are orders of magnitude higher than the SE signals. Photomultiplier tube cannot amplify BSc signal. We don't even, this is also not the case, right? The photomultiplier tube easily can do those things. Now, BSc are generated close to the primary beam. This is right. But ET detector is placed at an angle to optimize the secondary contrast. See, what we have saw that, let us say I am putting my ET detector over here. And this is my specimen. From specimen I am getting the secondary electron. I am also getting the lot of backscattered electron. BSc signal. Some BSc signal can also go over here. Some can go. Why we are not keeping it over here? We are keeping it at angle so that we can change the, we can get the SE electron. If I place it somewhere over here, if I place my ET detector at certain angle, what I will get mixed signal of BSc, SC and BSc. We won't be able to tell that the contrast is coming from which one. Now by keeping at certain angle, we are minimizing the, if we are keeping at certain angle, we are minimizing the BSc efficiency. Because we know that BSCs are mostly scattered back in the larger fraction. By keeping at certain angle, now again we are giving the positive bias so that this SC can get attracted towards it. Now this SC will get attracted toward this particular thing. Having the low energy, it can come, but BSC having the high energy, it will not divert its path. It will go it will follow the way it should be. Okay, so the right answer here is option B. VSCs are generated close to the primary beam. So this is a primary beam. If it so the VSC signal which are generated, it will be very close to the primary beam. Okay, but the ET detector is placed at an angle to optimize the SE contrast. Now first one, BSC has too much energy for the scintillator to handle. It has not to do with the energy. If it is have more energy, we don't even need this bias, right? This 12 kV bias which we are providing, we won't even need that. So it is somewhere in the positive way. Okay, so the right answer is option B. Okay, okay guys, let me know if there is any doubt in this particular question that we have covered. If not, let's move ahead to the next question. Now, the SE signal is, sorry, the SE1 signal. Now we have to understand couple of stuff here. Let's see the optics of the SEM. At the top we have electron gun. After that, this is generating the electrons. Okay. Then we have condenser lens. After that, we have a scanning coil. Then it is followed by the objective lens. Then we have the specimen. Right. Now, when this particular gun is coming, like this electron signals are coming, beam, primary beam, it is going to interact with my specimen. So it will generate the signals. This, let's say this is my interaction volume. This is where it hit. Now up from certain angle, we'll get one more signals. So this is known as SE1 signals. Right now we are only talking about the inelastic scattering. Which is going to generate the SE signals. So spatially, if this is my incoming electron beam, here SE1 will be generated. Little bit far, SE2 will be generated. Now if I keep my ET detector over here, let's say over here, this is my ET detector at certain angle. What will happen? Let's say this is the SE2 and this is SE1. ET detector will have combination, it will detect the combination of the SE2 and SE1. Now we know that since we are getting from little bit far also, so what is happening that even though I focus my electron beam on small region, still I am getting the signal from the quite large region. What does it mean? It means that the resolution has decreased. You are getting the signal. You were thinking that you focus the we were thinking that we focus the electron beam at small region, so we should get the signal from the small region itself. But instead, what is happening? We are getting from certain the spread is there. We are also getting the SE2. We are also getting the SE1. So this is ET detector I am using at the angle. It is going to decrease the resolution. Now to overcome this, to overcome this, if someone only want to capture the SE1, if we remove the SE2, then what will happen? If what we were getting, that the combination of SE1 and SE2, if we remove the SE2, only signal we are getting from SE1, then what we can say that the resolution will increase, the resolution will improve. Now to do that, if I only want to capture the electron which is coming from here, what I will do, what one should do is that they will place a in-lens detector. This is placed in the optical objective lens. Okay, so this in-lens detector has been placed in the objective lens. Now these electrons which are coming, they will get, in the influence of the magnetic field which is created by the objective lens, they will pull back, and here we will get the signals. So instead of detecting from the angle, we are detecting from the beam which are close to the primary beam, and now we are getting the better resolution. Okay, so this is how the entire thing about the in-lens detector is. If any doubt in these things, let me know. Okay, since there is no, let's try to solve this question. The SE1 signal is separated from the other SE plus BSE signal when captured in an in-lens detector. This is option A. Separated from the SC plus VSC signal when captured in the ET detector. Option B. Mixed with the other SC plus BSC signal when captured in the ET detector. Option C. Mixed with the other SC plus VSC signal when captured in the in-lens detector. What do you think? What is the right answer over here? Any idea, guys? So how we can separate the SC1 from the other thing? So here the right answer will be the separated from the other SC plus BSC signal when captured in the in-lens detector. If we are using the in-lens detector, then we will be able to separate it from the other SC and BSC signals. Okay, let's try to see if a few more others answers are right or not. Separated from the SC plus BSC signal when captured in the ET mode, ET detector. This is incorrect. We are keeping at certain angle, and we know that it is a combination of SE2 and SE1. Okay, so it's not going to separate. Mixed. The SE signal is mixed with the other SE plus BSC signal when captured in the ET detector. Is it right? This is right. The SE1 signal get mixed with the other SE and BSC signals when captured in the ET detector. So if I'm using this, what we are getting, it's a mixed information. Okay. So here the right answer is option A and option C. If any doubt in this, guys, let me know. If not, let's move ahead to the next concepts. Now, based on the stuff that we have learned over here, we have the condenser lens, we have the objective lens, below the objective lens, we have the specimen. Let's try to answer this. The final lens in the SEM column is called as, the final lens in the SEM column is called as, yeah, very good. Option C is the right answer. It's an objective lens. Okay, very good. So with that, we have solved this question number 6. Let's go to the next part. Now we are talking about the solid state BSC detector. Solid state BSC detector is made from the conducting material. Is it true? We have classified the material in 3 parts: metal, the conducting, insulating, and semiconductor. Among 3, which one is this acid detector? BSC detector, solid state BSC detector, can perform extremely fast scan during the image capturing. Is it very fast? Now let's go to the third option. Let's see the entire question first, then we'll see. Occupy very little space within the specimen chamber. It will occupy a very little space. And the first one consists of the single element. Single element. Now let's see it one by one. In the class we have saw that solid state BSE detector, it has total of 4 elements. It is somewhat more or less will look like this. And across this the beam will pass, the primary beam will pass. So it's not a single element, it's a 4 element. Occupy very little space. The answer is true. We are talking about the solid state BSE. This is right. Previously, like we have saw that in the long back, ET detector. By the way, ET detector is quite bulky. It's quite heavy. Okay, it will occupy more space. So this ET detector was placed just above the specimen, somewhere over here, and we are able to capture the BSE signals, okay, which was generated. So, but now due to its bulkiness, it was very difficult. Okay. So what people did that they changed it with the very light space, very like the solid state BSE detector, and it is having the very small little space it will take. So this is the right answer is option C. Now, can perform extremely fast scan during image capturing. The one of the disadvantage of this is that it is slow. Now why it is slow? Because it's not conducting, it's a semi-conducting. Since it's a semi-conducting, now the primary, this backscattered electron, it is going to the detector. Now this detector, it's a semiconductor material. Now it will, what will happen? The hole and the electron pair will be generated. This whole electron pair need to be separate out. Now they will, under the influence of the field, they will separate onto the other side of the detector, and they will contribute towards the generation of the signals, the final, which we are going to see in the screen. Now this entire thing, it will take a lot of time. Okay, and that is the reason why BSC detectors, whenever if you try to image, if you try to use the SEM, that too in the BSC mode, it will take long time to scan compared to the SE. So you can get the SE image in a couple of, let's say, in a minute. You can scan from the top to the bottom, one particular window. But in the BSC, you will take around something around 2 to 3 minutes. It will take to get the better quality, good quality BSC image. So it is slow, and it is semi-conducting material. Okay, so this is how it is regarding the solid state BSC detector. If any doubt, let me know. If not, let's move to the next question. Question number 8. The resolution of the SE image in SEM can be improved by using BSC detector, can be improved by using inlens detector, can be improved by using the high biased in the ET detector, can be improved by using the WDS detector. What do you think? What is the right answer over here? It's very easy. Like we have already solved this question. We have discussed a lot about this. More or less, you can see that this question is a repetition of what we have studied till now. Very good, Ahmed. The right answer is option B. It is the inlens detector. Right. So why, how it is happening, that we know that SE1 electron we are capturing on the larger scale, and that's why we are able to say that its resolution is improving. Very good. Now With that, we have solved these 8 questions. So we are done with the detector part. Now the important part about the resolution. And one more thing, depth of field. This thing we are going to discuss now. So here we can see that again, electron gun is there, condenser lens is there, scanning coils are there, objective lens is there, and the objective aperture is there. Then the specimen. D, the first equation you can see, this D, it is a probe diameter. This probe diameter, like this is a spot of the electron beam which is going to hit the specimen. So let's say this is the size. So electron beam size is like this, something like this. This is D. This is D naught. Okay, somewhere over here, yeah. D naught will come to the D1, then D1 will come to the final position. Okay. Now the important thing is that U1, which is the distance between the condenser lens and the gun, electron gun, V1 is the distance between the condenser lens and its focal point. U2 is a different distance between the secondary this generated image, which is going to act as a source for the objective lens. This image of the image of the probe electron, this is going to be act as a object for the objective lens. Now from here, this focal point of the condenser lens, from here to the objective lens, this distance is U2. And the distance from the objective lens to the specimen, always remember, this is very important. The last part is very important. The distance between the objective lens and the specimen is the V2, which is known as the working distance. Okay. Now, what is our aim? We want that D to be as small as possible. If D is small, then what we can say that our resolution will be improved. Resolution will be improved. Right. So our aim is to get D as small as possible. Now using the formula, lens formula and all, what we have obtained that D is equals to the D naught V1 divided by U1, this ratio, and V2 divided by U2, this distance. Okay. Now consider this formula. What will happen if I decrease the working distance? If I'm decreasing the working distance, what is happening that if D working distance is decreasing, then D will also decrease. Right? The probe will decrease. What I mean by decreasing the working distance? If the lens is over here, if this was the objective lens, and this is the specimen, and we are getting the some signal. Sorry, we are passing the electron beam. This is the case 1. In the case 2, what we did, we strengthen the we decrease the working distance. Now in according to that, it will focus at this different point, because now the distance has decreased. This distance was more. Now we can see that as we keep on decreasing the size, keep on decreasing the working distance, what is happening to our beam? Initially, let's say it was like this. Now after a while, when we are decreasing it, it is going to be like this. Right? This is how it is changing. This is what it is changing. So now what does it mean? We are converging. The convergence power is more. We are converging it more. We are focusing it to a single point. Here they are converged more compared to this one. This is what is happening. If I keep on decreasing V2, this D will decrease. Now, one more important part people talk about that the condenser length strength. So more is a condenser length strength. More is a condenser length strength mean that it will converge even more. So instead of converging, if let's say it was converging at some this particular point, the electron beam it was converging at this particular point. What will happen if I increasing the strength? It will converge at this particular point. So this alpha, let's say alpha I and alpha f. So what is happening that the alpha f is increasing, then and alpha, then the I. So we keep on increasing the angle, we keep on strengthening it. We are trying to condense the electron beam more and more. And if it was this was the height at which it was converging, this height will also decrease. Okay. So what we are doing, we are decreasing the V1. We are strengthening the condenser length. It means that we are decreasing the V1. So if we are decreasing the V1, okay, if we are decreasing the V1, again the probe diameter will decrease. Okay. So you have two way by which you can control the probe diameter. One is that you can decrease the working distance. Another is that you can decrease this particular, you can increase the strength of the condenser lens. Now, this part is clear. Now let's go to the second part, depth of field. H is the depth of field. What is this? What is depth of field? Let's take two scenario. In one case, the specimen is like this. In another case, like both the cases, the specimens are same. In one case, we are able to focus. Let's say you took your camera, normal scenario we are talking about, not the SEM now. You were trying to focus this particular region, let's say. You are trying to focus this particular region. So what happened? Along with the focusing this, you are able to focus. You are able to see, let's say someone was standing here and some car was passing by. So you are able to see this also. Okay, entire thing you are able to capture in your camera very nicely. What was not captured is this region was not captured. So this is what we call the region which is in the focus, like the depth by which it's in the focus. This is known as the depth of focus. Let's say T1. In the second case, someone was able to capture this much. They are able to see the entire thing. Okay, so what we can say, this is D2. Let's say this is D2. So depth of focus here. So in the case of D2, we observe that depth of focus is more than D1. Right. So here you are able to focus entire. Now one can ask you that in the portrait, like when someone tell that take my portrait pic, what does it mean that you have to focus only on that particular person. If something is there onto the back, something is moving and all those things we are not going to consider. Our aim should be this. So in that case, what you will do, your depth of focus will be very less. While if you are going with the geographic environment, those the climate type of peak, normal peak, in that case, what will happen? You will use the depth of focus should be high. You are going to cover the entire thing. Okay. So this is how it is. So the formula says that here the formula says that this S is constant over here. This is the pixel of the screen on which we are recording things. Now, like the pixel of the image, this is the working distance. So depth of field is depend upon the working distance. Magnification, this is the aperture diameter. A is the aperture diameter. So we have the objective lens. But we know that the spherical aberrations will be there. So to overcome that, to remove the spherical elements or to minimize it, we cannot remove entirely. To minimize it, what you will do, you will use the aperture. Now, since we are using the aperture, by that way we can minimize the spherical aberration. Now, this is the diameter of that particular aperture. Now, let's try to talk about the depth of field. If I keep on decreasing the working distance, if working distance is decreasing, depth of field is decreasing. So, if your specimen is rough, but you are only able to, since your depth of field has decreased, you are only able to focus the small region of it. You are not able to focus the entire region. So, in that case, the specimen which are rough, you cannot use it because you are decreasing the depth of field. Now, let us say someone want to do the factography. Factography usually have the very rough microstructure, like the hills and valleys will be there a lot. In that case, what you should do, you know that you want more depth of field, you want to focus a lot. In that case, what you will do, you will increase the working distance. Now, you know that now the both thing is there. If you increase the working distance, your resolution will go down, but if you increase the working distance, your h will go up, right? So one need to play based on their material, and the optimization is always needed. Magnification is also, if you need more magnification you keep on increasing. In that case, what will happen? Again, the depth of field will decrease. Okay. Aperture area, if the aperture diameter is increasing, depth of field will decrease. So we can remember these things entirely. And based on this thing that we have learned that about the depth of field and depth of focus, sorry, depth of field and resolution. Based on that, let's try to solve few questions. Before that, let me ask you: do you have any doubt in this particular thing, in this entire discussion that we have made? Okay. Since there is no, let's move ahead. Let's go to the question.
Here only one doubt. Here we cannot increase both together, right? One we need it with, one we need to compromise. Am I right or wrong?
Yep. Yeah, it will happen. We cannot improve both of them together. Yeah. So now, let's try to solve questions. What is the effect of inserting a small aperture in the objective lens? You are inserting an aperture. What aperture will do? It won't let, it will decrease the spherical aberration, right? It will decrease the spherical aberration, but how it is doing? If this much amount of spread was there, this much amount of electron beam was coming, and the aperture is only allowing this, so what will happen? The spread will be minimized. It will only allowing the part of, if this was the electron beam diameter, it is only allowing the part of it to pass through. Okay. So what it is doing, that the current is also decreasing. So beam current, if I am inserting the aperture, so beam current is decreasing. Okay. It is very important because it's the electron beam which is going to interact with the specimen, is it's going to generate the signals. Okay. Let's try to now let's read the options. What is the effect of inserting the small aperture in the objective lens? First one, it increase the beam current and reduce the spherical aberration. Decrease the beam current and reduce the spherical aberration. Next one, increase the beam current, increase the probe size. It has no effect on the beam current and but improve the resolution. What do you think? What is the right answer over here? A, B, C, or D? So Ahmed, we just now told that smaller aperture, like we are inserting the aperture, right? Yeah, very good. Right answer is option B. So if you are inserting the aperture, it means that the beam current will go down because you are blocking certain this region, the electron which was coming from this particular region. Now it has been blocked, and so it decreases the beam current, and the entire its most significance is that it will cause the reduction in the aberrations. Okay, very good. The option B is the right answer. Let's go ahead. The distance of the objective lens to the specimen is known as object distance, working distance, focal length, crossover distance. The distance between the objective lens and the specimen. What's the right answer? Very good. The right answer is option B. So this distance is very important. The distance between the objective lens and the specimen is very important because in SEM, if you are not able to focus, if you are not able to do something which you wanted to do, this is one of the function, this is one of the handle by which you can alter the optics, and you can increase the, maybe let's say, resolution. If you are decreasing the working distance, you can increase the resolution. If you are decreasing the working distance, again you are compromising with the depth of field, right? And if you are increasing the working distance, the depth of field will be improved. You are able to focus the entire section even if it is rough and all, but still you are going to compromise with the resolution. So by playing with the working distance, you can get the image. The strength of the operator lies how and when they are changing this particular working distance, and also the strength of the condenser lens. Okay, now let's try to solve the question by 11. But before that, I should tell you one thing. The purpose of this entire three lenses. So what we have electron gun, then we have condenser lens, then we have scanning coil, after that we have objective lens, in the specimen. Electron gun, we know its function, that what it is doing, it's generating the electron beam. Condenser lens, it is used to condense, the word itself, condense. It is used to condense this diameter, probe diameter. Scanning coil, it is used to deflect electron beam. So let's say the direct beam is going on like this. So but you want to focus this region. So what you will do, you will change the strength of the scanning coil, and you can move from here, you can move it to here. You can focus the region of your interest. Okay, so this is a scanning coil. Now objective lens, it is used to, again, it's used to focus the electron beam on the specimen surface. See, from this particular figure, its focal point of the objective lens will lie over here, because the beams are converging. Where they are converging with, they are converging to the specimen, they are converging to the specimen surface. Okay, so the objective lens purpose is to focus the electron beam onto the specimen surface. Let's try to solve this question number 11. True and false. First one, the scanning coil are placed between the condenser lens and the objective lens to ensure the deflection still pass through the optical axis of the objective lens. What it's saying? Very good. The right answer is, this is true. Let us say I am drawing the lenses by this. This is objective lens. This is your specimen. Now in the image, in this particular thing, we have saw there is a two coil, scanning coil 1 and scanning coil 2. Let's say this is coil 1 and this is coil 2. This is the electron beam which is coming. You want to focus somewhere over here, let's say. So what first we'll do? First we'll deflect it corresponding to this particular region. The second will make sure that it should pass through the center of this particular objective lens, so that we can focus it over here. Okay, so the entire purpose is that, so what they are doing, the combined action is to deflect and to make sure that the optics, like the beam, should pass through the optics axis of the objective lens. Okay, right. So if someone can ask that, okay, what will happen if my objective lens is over here and after that I'm using the secondary coil? You will be only able to focus in the objective lens. After that you won't be able to focus, right? Now if it is going to deflect, you won't be able to focus. Since you want to focus it, that's why the arrangement is like that. Okay, objective lens should be at the bottom, should be the last one. And this is true. Very good, Ahmed. The B part. In the SEM, changing the strength of the condenser lens alter the working distance. Is it true? Yep. Changing the strength of the condenser lens. By changing the strength of the condenser lens, we mean that the V1, that is, if we are changing V1, will it affect the working distance? In SEM, changing the strength of the condenser lens alter the working distance, V2. V1 will affect V2. Is it true? SEM, changing the strength of the condenser lens. If you are changing the strength of the condenser lens, working distance, it's a false, right, Ahmed? Because see, the specimen is how you can change the working distance. The entire this thing V1 plus U2 is constant. This is not going to affect the working distance. Okay, if questions would be like, if instead of the strength of the condenser lens alter the working distance, instead of working distance, if I would have write that the probe diameter, then it would be true. In the present case, it's a false. So how you can alter the working distance? You have to move the specimen stage. Good. So now let's go to the third part. Decreasing the working distance, V2, by moving the specimen closer to the objective lens will result in the larger final probe diameter. The probe diameter will increase. They're telling that, okay, decreasing the working distance should lead to the larger final probe diameter. Let's see. V2 we are decreasing, working distance decreasing, V2 decreasing. If we are decreasing V2, that is working distance, so what will happen to the probe diameter? D will, working distance is decreasing, if this is decrease, so D will also decrease. So what will happen? Resulting in a larger final probe diameter? No, false. It will be smaller. Right. Now the last part. The aperture in the objective lens is used to increase the beam current and improve the image brightness. The aperture in the objective lens is used to increase the beam current. If you are using the aperture, beam current is increasing. Like the question is saying that, okay, if you use aperture, beam current will increase and improve the image brightness. True or false? We have discussed about similar question few minutes back. If you are using aperture, what you are doing? If you are using the aperture, it means that you are blocking the electrons, right? Very good, Ahmed. This is false. Okay, very good, guys. Let's with that we have solved the question number 11. Let's go to the question number 12. In SEM, a smaller spot size will require higher brightness and contrast level in the detector. A smaller spot size will require high brightness and contrast level in the detector. We are talking from the detector perspective, okay? Think from that perspective. A smaller spot size will require low brightness and the contrast level in the detector. So what is happening? See, if the smaller probe size, a smaller spot size is there, why it happened? It is happened because you use the aperture. If I'm using the aperture, I will what I'll do, I'm blocking the electron beam which was there. I narrow it down, so it meant that less number of electron. So your specimen, the specimen which we are trying to analyze, since the electron beam, the beam, it was having the low electron, so the signal generated will not be that much, right? Okay, so the less number of electron will be generated. This will also be reflected in the signal. So now if you want to detect this thing, what you will do, your detector should be in the higher brightness and the higher contrast mode. Then only you will be able to see these images. But if it is in the low brightness, low contrast, everything will be dark. Okay, like it means that it should be more sensitive towards the electron beam. Sorry, it should be more sensitive toward the incoming signal, SA signal or BSC signal. Okay, the smaller spot size which was coming due to the we use the aperture diameter we keep on decreasing, number of electron beam that is passing through the aperture is decreasing, which is interacting with the specimen, so the number of signal which is generated in the specimen is decreasing. So now if you want to detect those less number of signals, we need more brightness. It should be the detector should be more bright, should be more sensitive toward it. Even the small number of electron, less number of electron, it should be able to detect. It should be in the high brightness and the contrast level in the detector. Right? So the right answer is option A. Any doubt, guys, in this particular entire explanation that we have made? Okay, since there is no, very good. Let's move to the next question, question number 30. A smaller working distance in SEM. So now working distance we are decreasing. What and all things are going to happen? Let's see the which parameter the question is going to talk about. A spatial resolution. A resolution means that they are talking about the D due to the decrease in the probe diameter. Lower spatial resolution due to increase in the probe diameter. Increase spatial resolution to increase the probe diameter. Lower the spatial resolution due to decrease in the probe diameter. Let's not read too much. All we got to know that okay, working distance is there and we have to relate with the probe diameter. So how it is? We know that if we keep on decreasing the working distance, our probe diameter will also decrease. Right? Now this is since the probe diameter is decreased, it means that spatial resolution has increased. Smaller the probe, more the spatial resolution, right? So let's try to answer which one. Small working distance is smaller, increase the spatial resolution due to decreased probe diameter. The right answer is option A. Let's go to the second one. Lower spatial resolution due to increased probe diameter. No. Increase in the spatial resolution due to increase in the probe diameter. No. Lower spatial resolution due to decrease the probe diameter. So probe diameter is decreasing, but spatial resolution is also improving. So the Right answer is only A. Okay. This is how we have solved this question. Question number 30. Let's try to solve few more questions. Okay. Just two more questions are left. The smaller aperture in the SEM. The smaller aperture in the SEM will result in. Okay. Smaller the aperture. What do you think? It's very easy. Give a try. Aperture is small. Smaller probe size with high probe current. Larger probe size, low probe current. Smaller probe size, low probe current. Okay. Larger probe size, high probe current. If I am decreasing this aperture size decreasing, it means that the probe current is decreasing. Okay, the number of electrons, it is decreasing. Now, but also with a smaller aperture, you are increasing the probe diameter. Probe diameter is also decreasing, right? So what we can say, a smaller aperture, a smaller probe size, high probe current, no. Larger probe size, no. A smaller probe size, low probe current, right? So the right, yeah, very good, Evan. The right answer is option C. Okay, great. Now the last part. The discrete beam location on the specimen surface from where the signal is generated are called. We have specimen surface from where we are generating the signal. So we are generating from particular region. We will focus at one particular region and then we will collect the information from that. What that location is known as spot, pixel, index, raster. Very good. The right answer is option B. It's a pixel. So that's why we are saying that it's a pixel by pixel. So one pixel over in the specimen will correspond to the one pixel in the screen or in the image. Right. So this was the list of the question that we have to discuss today. And okay, let me let me know if you have any doubt in the entire thing that we have discussed. Also, if there is anything that has been covered in the class and that is not understood, that was not clear yet, if you have any doubt, please let me know. We can discuss that thing.
The formula you written, no? Depth of field. And there, 2S W field MA. M is magnification. A for it is something different, or it is MA for the magnification.
M is there and A is there. M is magnification, A is aperture diameter.
What's the
Yeah. Okay. Any more question, guys? If not, then we can wind up today's session. And so this week we keep our this dot solving session on at 6 to 8 on Friday. But next week we'll come back to our time and we'll do it at 3 to 5 p.m. Around on the Saturday, every Saturday. Okay.
okay.
Yeah. Okay, guys. Great. So bye bye. See you in the upcoming week.